Hey everyone, Mr. Ray here with our next lesson in calculus. What we're going to do today is we're actually going to start a new unit. So in the real course, this would be the second to last unit, Unit 8, which is curve sketching. So this is a pretty important unit. Um, there's 4 lessons in this. Um, so what I'm going to try to do is do 2 of the lessons this week, so one Wednesday, one Thursday, and follow that up next week with the remaining 2 lessons on Monday and Wednesday, um, something like that. But like I've told you guys, there's no assignment this week. I wanted to kind of start and finish curve sketching, and then give you a nice assignment on the complete unit. So instead of doing partial things like we've been doing, um, we'll just wait for the next assignment once we're done curve sketching, and then we're going to wrap up the course with some optimization, some application questions, which is from Unit 9. Okay, um, so curve sketching is it's what it sounds like. It's how do you take a function? Now we're going to stick strictly with polynomial functions, and most of the time that's what we do in this unit anyways. But you could apply that to exponential and trig functions as well. Um, so you get in advanced functions, we did a fair bit of curve sketching for rational and polynomial. We are doing rational as well, so rational polynomial. Um, so you did learn quite a bit in advanced functions, and many of those tools we're gonna continue to use when we want to come up with a really accurate sketch of a polynomial or rational function. But we're going to add some new tools from calculus. They're going to help us do a better job of sketching. Okay, and some of that you've seen already. And this lesson kind of takes some of the stuff we've talked about before and puts it into practice. So um, in terms of some of the definitions, nothing too new here. Interval of increasing, a function f is increasing on an interval. Basically, if the y value um, of the second point or the greater value of x is sorry, if the y value continues to increase as x increases, basically that's what this means. Decreasing, it's the opposite. As x increases, f of x or y is decreasing on that interval. So we're going to be defining what are the intervals of increasing and decreasing. Critical points, and we're going to advance this later on in other lessons. These are points that help define the shape of a function's graph. So obviously um, a very important critical point would be a point where like a local min or max. Okay, and that's what we talked about here. Those aren't the only critical points. We'll talk about some other ones, I think in lesson 3 it is, um, once we get into second derivatives. Um, so, um, so what we're going to be doing is finding where these uh, these functions are increasing and decreasing, and we're going to be able to break that down a bit into, first of all, finding where the slope of the tangent is 0, and then testing the slope of the tangent to the left and right of those critical points. Okay, so this is pretty obvious. Slope of a tangent on a point of a section of curve that is increasing, the slope is always positive, and the slope is negative when the curve is decreasing. Okay, so we're going to use that in terms of, it's not talking about the slope, but the derivative of a function. Okay. Now, most of the time, this is always going to be true that f of x will be continuous and differentiable at all the intervals, and that's true of any polynomial function. But what happens when you have rational functions is it may not be differentiable at some points or may not be continuous at some points. because things like vertical asymptotes or holes, basically that's where you have to pick up your pencil. Um, so um, yeah, so let's go down to these three here. Basically, this is where we apply the derivatives. Okay, if f prime of x, if the derivative of f changes from negative to positive at a point C, then C is a local minimum. Okay, and if it goes the opposite way, if the derivative changes from positive to negative, so you could think of it this way: positive to negative means it's going up, and then it changes to going down. Well, that point would be a local maximum, and the one above there, it's going from negative to positive. That's a local min. Okay, now what happens when you have this point C and it doesn't change the sign? Say it's going like this. Okay, well that point is, well, it's negative. The derivative is negative on both sides of that point, so it's not a local min or a local max. Okay, it's got to change from one to the other, negative positive or positive to negative. Okay. So we have the cubic here. First example, f of x is x cubed plus 3x squared minus 2. How did we sketch this graph in advanced functions? Okay, so hopefully most of you will remember that. So what we did is we used the factor theorem to find the zeros. Now, for this, we'd use the factor theorem once maybe and find one factor, and then use the synthetic division or long division to find out what's remaining, which would be a quadratic. And then once you've gone down to a quadratic, you can use factoring, your regular factoring of a quadratic or quadratic formula to find the zeros. The other thing we did in advanced functions was look at the end behavior as x is approaching negative infinity or positive infinity. What's happening to the value of y? It's either going to positive or negative infinity, so you can get your end behavior. And then by combining, and the way we get the end behavior is from the leading coefficient, whether it's positive or negative, and the degree of the polynomial. Right? The degree was important because even or odd would define its shape. Either, like a quadratic is, it's going to open on both ends towards the same direction, and the end behavior will help define is it opening down or is it opening up. Okay, so that would be a even degree polynomial. Odd degree polynomials could look like this, or they could look like this. Okay, so that's what we did in advanced functions. And then at the end, once we've kind of got the shape, if you remember, we kind of know it's, we get a vague idea of what's going on. We get the zeros, we get, it goes up and then it comes back down through this zero, or it bounces at this zero. But in terms of the local min or max, it's all guesswork, really. Well, not totally guesswork. So for the local min and max values, usually they lie halfway between the zeros, but in terms of, well, what's the value of y, we have no idea. Does it go way down or does it just go down a bit? We'd have to actually plug in the value to get that. So we didn't really do a whole lot of that in advanced functions. We were more concerned with the end behavior and the zeros and what's going on between the zeros. Okay, so what are we going to do in calculus? Well, that's an excellent question. So let's look at this. So I'm not going to rewrite that function, but if I was to take the derivative of f of x, that would be 3x squared plus 6x. Okay, now what we do, if we want to find the zeros, we set that equal to 0, and then solve for x. What values of x make the slope of the tangent 0? So one thing we can do here, factor out 3x. and we get x plus 2, and that tells us that the values of x that have a horizontal slope, or a slope of 0, are 0 from the 3x and negative 2 from this second factor. So we know we have two critical points at 0, negative 2. Now, we don't really know, we'll get into this later part in this, but we don't know at this point, is it a local min or max? We know they're critical points, and it doesn't, like we've said in the introduction, it may not be a local min or a max. It might be neither. So we'll talk about that when we get there. So we could say at this point there's a local min, max. Well, I guess I'm kind of contradicting myself when I say this. More generally, there's critical points. Critical points, and that is going to occur at 0 and negative 2, and if we plug these in back into the original function, we get, well, that one's easy to get. Negative 0, negative 2 is the first point, and if I plug a negative 2 back into here, I get f of negative 2 is 2. So these are the two critical points of this function. All right, it's important to know, is the function continuous? And we talked about this earlier. Since that's a polynomial function, it's continuous everywhere. So the answer is yes, it is a polynomial function. If it was rational, there would be points where it's not continuous, and you have to watch out for that. Okay, now here's where it gets more interesting, and this is the whole point of this lesson here. What are the increasing and decreasing intervals? And from that, once we answer this, we'll be able to tell, are these points local mins or max or neither? And we can do a sketch at the end here. Okay, you're going to see in this unit we make pretty extensive use of these charts. Okay, and they're quite useful. So I would encourage you to go along with this. So I'm going to have 4 columns here. This. Okay, so I'm going to have my values of x along the top, and then I'm going to have 3. So the reason why I have 3 columns is because I have 2 critical points. So for each of these values of x, negative 2 and 0, I'm going to develop intervals around there. So my first interval will be from negative infinity to negative 2. And then the next interval is between the 2 critical points, so between negative 2 and 0. And then finally from 0 to positive infinity. And then you could kind of consider, well, the breaking point here, because these never include the actual value, because the actual value is a 0. So what makes this more valuable, we could actually put the value of x along this line where the actual critical points are. So we have a critical point at negative 2 and a critical point at 0, and then the intervals around those 2 critical points. Okay, in the next, now you're going to see the next 2 columns are really the same thing, but let's go with this. So this will be the sign of the derivative, sign of dy by dx, or f prime of x, whatever you want to call it. Okay, so just a reminder, maybe I'll write it over here. So f prime of x, and I'm going to put the factored form of this. It's equal to 3x times x plus 2. Okay, now if you remember this interval testing, we're going to do interval testing here. So I want to know what's the sign of the derivative here, and actually that's going to be tell us whether the function is increasing or decreasing, which we're going to put here. So slope of tangent, it's really the same thing. And then we're going to do a more visual. Is y increasing or decreasing? Okay, so they're all related, but as we're learning this, it's not a bad approach to it. Okay, so remember for these intervals, we have 3 intervals. We're going to have a test value for x. So anything less than -2 would be a good test. So I'm going to put a -3 here. Maybe I'll circle these numbers here. And then there's a bullseye there. Something between -2 and 0, not a lot of choices. So -1. And then anything greater than 0, why not 1? Okay, so I'm actually going to plug in -3 into the derivative. So f prime of -3. All I care about is the sign. So I look, and that's why I have the factored form, because it's a lot easier to get the sign quickly. So if I plug in -3 here, that's going to be negative, and that's going to be also negative. So basically I have negative times negative, because that's going to be negative, that factor is negative. Overall, for that interval, it will be positive. The derivative is positive in this interval. If we do the same thing here, we plug in -1, well, negative for the first factor, but this will not be positive, so we have negative, positive. If we multiply that together, we get negative. And then over here, if I plug in 1, you can see both of these are going to be positive. So positive, positive equals positive. So I have two intervals where the sign of the derivative is positive, and in between them, that interval is negative. So with the slope of the tangent, well, it's basically the slope of the tangent here will be positive. Slope of the tangent here is negative. Slope of the tangent here is positive. So that means increasing, decreasing, increasing. Okay, and to make it more visual, I could just put up to the right, down to the right, up to the right. Okay, and why we do this, because you could really say, well, these 3 things are all the same. It's just a different way of interpreting them. I don't think you really have to put both of these. You could just interpret that positive as increasing. Okay, but where this becomes useful, because this line here is the point -2. So at this point, you could see, well, to the left of -2, the function is increasing. To the right of -2, function is decreasing. So therefore, this point, this critical point at x equals -2 must be a maximum. Okay, same idea for this critical point at 0. You can see to the left it's decreasing, to the right it's increasing. That means here this is going to be a local min. Okay, and that's where that becomes useful. Okay, and then finally just a sketch. Okay, and this is just a sketch. Okay, so I'm not, we could do the zeros, and we will later on. Where does the function actually cross the x and y intercepts and stuff like that? But for the point of this, I'm just going to work with, can't see it anymore, the 2 critical points here. So I have a critical point at 0, -2, and another one at -2, 2. So there's my 2, let me move this up. There's my 2 critical points, and now from this little exercise here, well, it's kind of obvious, but it shouldn't be, because we really don't know the end behavior, because we haven't even looked at that really, like we did in advanced functions. But we do know that this point here at -2, well, that happens to be a local max. So we can draw a little curve opening down, and this is a local min, so that's a curve opening up, and then we can just basically, continue with what we're going here. And since there's no other critical points, that means there's no turning points. So you don't, you know that this is going to be positive for that entire interval from 0 to positive infinity, and this will be negative from -2 to -infinity. So there's no worry about, well, aren't we just looking at this interval? No, you looked at the whole thing. You found out that the only values where you have a slope of the tangent is 0 are at 0 and -2. Okay, so this little exercise here is very valuable, and we're going to extend this to second derivatives later on. So it's important that you practice this for this lesson and make sure. The important thing is, you know what's happening at the intervals between the critical points, and from that you can derive, oh, that critical point is a local min, or that critical point is a local max. Now, there could be, you can see both of these critical points had increasing slope on one side and decreasing on the other. Okay, so it had to be a min or a max based on what you're seeing there. But it is possible to have two neighboring intervals with the same positive or negative. So it's conceivable that, well, maybe this one might be negative, so it's going down too. So what's happening at this critical point? Well, it's not a local min or a local max. It's going to be neither. Okay, so we'll see that I believe in another example coming up. Okay. All right, so here we do have our rational function. So for this function f of x equals x over x squared plus 1, determine the local mins and maxes and the intervals of increasing, decreasing using derivatives. Okay, so now if I'm taking the derivative of f of x, I could either do product rule or quotient rule. I could change x squared plus 1. I could put brackets around it with a -1 exponent and then just use product rule. But again, it's your whatever you prefer. Like I've said before, the problem with the product rule is if you use an obvious quotient question and adapt it to the product rule, well, you're going to pay the price down the line by having to do a fair bit of work simplifying your answer. So I'm not going to really choose one or the other, but if you could tell, if you use quotient rule, well, the derivative function f prime of x, the bottom part will be x squared plus 1 squared, and the top part will work out to be, I won't do this, but -x squared plus 1. And you'll get this either way with product rule or quotient rule. So that's the derivative function. We want to set this to 0 now because we want to find where are the horizontal tangents, meaning the slope is 0, meaning it's a critical point. And we want to find these points now. So if I set the derivative to 0 and solve, hopefully you remember, if you have something like this with a rational function, well, you could do cross multiplying in that, but really if this right side here is going to be 0, that means that the top has to be 0. I think it's a nicer way of looking at it. And you don't even have to bother with what's on the bottom. So in this case, 0 would be equal to -x squared plus 1. If we add x squared to both sides, we get x squared equals 1, which means x could be plus or minus 1. So I have two critical points at +1, x equals +1, and x equals -1. So let's do our table here. So it'll be the same size as before because we have two critical points again. So I'm going to have 4 columns and 4 rows, I guess, too. Okay, so the top will be my values of x. Okay, now that you know what these lines mean, I can actually put these values up here. So that line represents -1, this is +1, and then my intervals in here, -infinity to -1, -1 to 1, 1 to +infinity. Put circles around there. I could pick my test values now if I wanted to. Let's do a test value of -2 there, 0 here, and 2 here. You could, I mean, the only one that you don't have options for is this one here. 0 is always the best test value anyways. So if I want to do my sine of dy by dx, and you can put your whatever titles you want here as long as they make sense to you. So I'm looking at positives and negatives. Now, if you notice the derivative function, the bottom, the denominator, will always be 0. Okay, sorry, it'll always be positive, because the worst this could be would be 0, and then this is always going to be something squared. So it's never going to be 0 on the bottom. It's never going to be negative on the bottom, so it's always positive. So all I have to really worry about is what's going on the top. So if I plug -2 in here, that's going to be -2 squared, which is 4. Put the negative sign in front, -4 plus 1. I'm going to have negative over positive, which is equal to negative. Okay, and I could do the other ones as well. I'll put my positives in right away. If I plug in a 0 up here, I'm going to get a 1, which is positive. So overall, that interval is going to be positive. And, you know, it seems like most of the time it kind of changes from one side to the other, but like I hinted at the last question, that's not always going to be true. So if I plug in 2 here, again, I'm going to get the same values if I plugged in -2, so that's going to be negative as well. Okay, so overall, if I want to talk about slope of the tangent, well, negative, positive, negative, and if I want to do, you know, is y increasing or decreasing? Well, you can see right from there that's decreasing. So let's make it more visual. That's going down, that's going up, that's going down. Okay, and now when you look at your critical points here, -1, well, that has to be a local min, and this one has to be a local max based on what's going on, whether the intervals to the left and right are increasing or decreasing. Okay, so that's all we had here. Now, in terms of should we figure out the y value, unless it asks you to do a sketch, like the first example did, I think it's good enough to say you have a local min at x equals -1 and a local max at x equals 1, because that's what it's determined, the local mins and max and their intervals of increasing and decreasing. So this chart has done everything for us to answer the question. Okay, let's go to something a little more higher degree. So in this case, it's quartic. Let me get this a little straight for you. Okay. For this quartic function, determine all the critical numbers and determine whether each is a local min, max, or neither. Okay. So same thing we've done before. So this is back to a polynomial. So f prime of x is equal to 4x cubed, and that's going to be -24x squared and plus 36x. All right, now if you want to find the zeros, this one we're a bit lucky because, you know, we got x's in them all, so definitely I can factor out 4x. And what do we have left over? Well, that's x squared minus 6x plus 9. Well, that worked out pretty nicely. Oh, sorry, that's, yeah. And I might as well just save a step here rather than writing that. Let's set that to 0 now. But we still have a quadratic here, so that's easily factorable. That's actually a perfect square trinomial. X minus 3 squared. Okay, so we actually have two critical values at x equals 0 and x equals 3. Okay. Now let's do our table. So break this into 4 that way and 4 this way. Now, the reason why I'm saying 4 all the time is because so far every question we've had has 2 critical points. If I had another one, there'd be another column over here. Okay, same number of rows each time, but different number of columns possibly. So we have our x, and we have sine of dy by dx, slope of tangent, and is y increasing or decreasing. Okay, now again, I got 0 and 3, so I could put those on the border lines, and then my intervals will be to the left and right of those values. So negative infinity to 0, 0 to 3, 3 to positive infinity. Test values, I could do a negative 1 here, I could do a 1 here, and I could do a 4 here. Doesn't pick anything you like. We're just interested in the sign. So I'm going to go with the factored form here. So when I plug in negative 1, I get negative. And this is always going to be positive, this one, right? Because it's a number squared. And it's not going to be 0 because we're not going to plug in 3. So this will always be positive, so it really depends on this. So I plug a negative value in, it's negative times positive. So let me do it this way, negative times positive, and that's equal to negative. And if I plug in 1, well, that 4x is now positive, that's always positive. Positive, positive is positive. This one here, and plug in another positive of 4, well, that doesn't change, right? It's still positive, positive equals positive. So here's the case I was talking about, because now your signs are not alternating in neighboring intervals. You have two intervals beside each other that are both increasing. Okay, so what does that mean? This is where the graph comes in handy. Not the graph, this visual part here. So down, up, and up. Okay, so you know that this is a min at x equals 0, but this is neither. Still a critical point, but it's not a local min or a local max. Okay, now if you're to do a quick sketch of this, you'd see, well, let's assume that I got my values for there, so that would be 0, 0. Yeah, and if I plug in a 3, actually I'm not sure. Don't really have to know what it is. It's going to be a fairly big positive value. Okay, so I'm going to have my point 0, 0. I'm going to have my point 3. Well, I should have spent some time figuring it out, but it's going to be, say it's up there. I'm not even going to bother putting a scale here. So at both of these points, I have slopes of 0. So actually, the best thing to do is I'm decreasing to this value, so I know my graph is going down there, and then it's heading back up. Now, here's where it's interesting, because it doesn't go back down after this point. It kind of does a little kind of time warp here. It does a little bit of a bend and then heads back up. So, and you see that with quartics, so not quartics, with cubics all the time. Okay, it doesn't pass, it does a little wobble as it goes through. So that's what that graph would look like. It didn't really ask us to do that, but I just wanted to show you what does it look like when it's neither. Because you can see if I actually did take the slope of the tangent there, it would be 0, just like it's 0 there. But you can see it's increasing on both sides. Okay, and that's what the neither means. Okay. All right, last couple. These should be quick. All right, determine whether or not the function f of x equals x cubed has a minimum or a maximum where the derivative is 0. So we kind of sort of looked at this a little bit, but so the derivative would be 3x squared. And so if you set that to 0, you get x squared equals 0. So x equals 0. So we have a critical value at x equals 0. And we probably already know what that looks like. Let's just pretend we don't. So this time I've only got one critical point, so I'm only going to have 3 columns, but still 4 rows. Okay, so I've got my x value, and I've got my one critical point at 0, and then I've got my intervals, so negative infinity to 0, 0 to positive infinity. Test values, well, doesn't really matter. I could do a -1 and a +1. Sine of dy by dx, well, if you plug in anything except for 0, if I plug in -1, that's going to be 3 times 1, which is 3. So that's going to be positive. If I plug in +1, I still get 3 here. So both positives. Tangent, both positive, and then so we're getting lazier with our notation here. That's totally okay. Now we know what this means. So in this case, they're both increasing, just like we saw in the last question. So what does that mean? Well, that x, the y value that goes with that is 0, 0. Okay, so it's increasing to the left, increasing to the right, but you have this little slope there of 0. So basically, it looks something like this. So get a little closer there. So, and that's exactly what, if you didn't know what x cubed looked like, you could kind of get that from, from the fact that that's a critical point, but it's neither, I guess I should fill that in. It's neither a min or a max at that point. Okay. Last question. Given the graph of the polynomial function, they didn't give it the equation, they just drew it for us. Graph f prime of x. Okay, so this is a little different. So if that's my original function, f of x, what I'm going to do, and you can see this very easily, you can find where the slopes, find where the critical points are, where the slopes are equal to 0. So I have a point here and here that are critical points, and that means the slope is 0. So if I'm graphing f prime of x, I know I have points at 0. So y equals 0 because the slope is 0 at 0 and 1. Okay. Now, what's happening to the left and right? Well, here you can see it visually instead of taking the derivative. You can see that this is obviously decreasing up to this point. So that means the slope of the tangent is negative. So it's going to be, now I'm not going to pretend that I'm doing a great job here, but I do know that to the left of here, f prime of x is negative because it's a decreasing function up to that point. Now between these 2 points, between x equals 0 and x equals 1, you can see the function is increasing. So that means my derivative graph will be positive between those values, and obviously it has to come back down to be at those points. So it's just a little bubble between them. And then to the right of x equals 1, it's decreasing again. So the graph of the derivative function will be going down, and you can see this looks very much like a quadratic, and in fact that's what it is. This original function, let me actually put the name of the graph. F prime of x is what I just drew in there. Yeah, you can sort of tell that this looks pretty close to a cubic based on what you learned from advanced functions. So the derivative function would be a quadratic because you're lowering the degree by 1. So the fact that our graph looks like that makes sense. Okay, so got a bunch of questions here. Don't expect you to go overboard with these, but I've got all the solutions for you, which I'll post, and try some of them out. Look at the questions that you can't get, see how I did it, and just be prepared for next test. Not this week, but the following week. Okay, so we're going to do 3 more lessons in this curve sketching, but this is the first lesson where you find intervals of increasing, decreasing, and critical points. You learn about those, and critical points are either going to be local min, local max, or neither. Okay? All right, guys, have a great day.